Welcome to the next video on design of beams. In this video, we'll be looking at check for web buckling. Now, since we have not covered design of compression member, these steps will be taken up in the next video. So, we'll skipping this check. We'll be directly taking the next step, that is check for web crippling. Check for web crippling. So now web crippling, in the sense, usually it will happen at the web flange junction because of concentrated load. So usually we have high concentrated load coming because of maximum shear force at the supports or any point load in between. So web crippling, the failure occurs at the web flange junction. Web crippling, the failure occurs at the web flange junction. So now directly we'll see the formulas as per IS 800. Clause number is not mentioned. We'll give you the reference for this clause number. Yeah, the buckling capacity, the crippling capacity as per IS 800 is Fw is equal to B plus N2 into Tw into Fyw divided by gamma m naught. Now here B is usually half the width of the support. B should be taken as usually the half width of the support, or else the whatever value is given to you. Here in this case, the width of the support is given as 200 and half of 200 is 100 mm. If value is not given, you have to take it as half the width of the support. If value is given, you have to take that value. Then N2 is the dispersion. N2 is the dispersion of the okay. The N2 is the dispersion of load from bottom of the flange to the top of the flange with an ratio of 1 in 2.5. So N2 is the dispersion of the shear force or the support reaction from bottom of the flange to the top of flange through the thickness of the flange with a ratio of 1 in 2.5. So therefore N2 becomes thickness of flange into 2.5. For every 1 mm vertical direction, the load disperses 2.5 mm horizontally. So the total horizontal load dispersion will be the thickness of flange into 2.5. So that is N2 is equal to 2.5 into thickness of the flange into Tw stands for thickness of the web, 11.2 mm into 250 mm yield stress of the web divided by gamma m naught, 1.1. So now Fw, when you calculate, you will be getting a value of 377.36 kilonewton. It means at a load of 377.36 kilonewton, your web will start crippling like this. Like this at this junction. Yeah. Now, but the maximum shear force coming at the support is 252.56 kilonewton. The maximum shear force coming at this support is 252.56 kilonewton. So whereas the capacity is 377. So 377 is greater than, or 252.56 is less than 377.36 kilonewton. So it is safe in crippling. The web will not cripple at the junction. Now check for crippling of the web at a load of 50 kilonewton. There is a point load of 50 kilonewton is also acting at the center. There is a point load of 50 kilonewton also acting on the beam at the center. Now this point load, now taking the same formula, so B plus N2 into Tw into Fy by gamma m naught. Now taking the same formula, this point load is acting at a single point. The point load 50 kilonewton is acting at a single point. So that is why your B is considered as 0 mm. The B is considered as 0 mm. Now coming to N2, so here it is taken as 2 N2 because this load will disperse on either side. Because the load will disperse on left side as well as right side. Like distribution of load, this will be similar to the distribution of load from a column to the footing. Yeah. Now if you ask me why it is taken on either side here, but only one side here. Now since this is the end of the beam, there is no dispersion taking at the the other side, the end side. The dispersion is taking only on the inner side. Now, since this is an intermediate, portion of the beam, hence beam is continuing this side as well as this side of the point load. Hence, the dispersion is taken on the both the side. The dispersion is taken on the both the side. That is why here for any intermediate point load that is at 50 kilonewton. So yeah, this width is bearing width is 0 mm because there is no, since this is acting at a point load and dispersion is taken on both the sides. That is why 2 into N2 and rest all things will remain same. TW into FYW divided by gamma M naught. That is 0 as it is. 2 into, yeah. So now N2 will be, already we know, that is 2.5 times of thickness of the flange. So that is 19.3 into 2.5 into thickness of web is 11.2 mm into 250 divided by 1.1. So now FW or the crippling load is 245.63 kilonewton. It means at this load, at this intensity of the load, your web will try to cripple like this. Here at a location of 50 kilonewton, at this intensity, your web will try to cripple at the top. But the load acting is only 50 kilonewton. At the top, the load acting is only 50 kilonewton. Hence, the load acting is 50 kilonewton, whereas the crippling capacity is 245 kilonewton. Therefore, it is safe in crippling. So, it is safe in crippling at the support also, as well as at the point load also. This crippling is mainly checked at the support because of high shear force. This crippling is mainly checked at the support because of high shear force or support reaction and at any other point loads. So now in both the cases it is safe. One thing you have to observe here. So now at the support we have to take this B equal to half the width of the support, or else whatever the value given. And N2, the dispersion, we should take only one side because the beam is ending here. There will not be dispersion on the other side. But if there is any intermediate point load, your dispersion will be on the both the sides. That is why we have to take 2 N2. So with this, we have to check for crippling of the load at the support reaction as well as at any intermediate point loads. Now I'll quickly show the reference where these formulas have come from. So now referring to IS 800, page number 67, clause number 8.7.4. We can see the same formula we have here. So FW is equal to B1 plus N2 into TW into FYW by gamma M naught. See, the same formula we have considered. B1 plus, sorry, the same thing, yeah. So B1 we have missed here. Is B1 plus N2 into TW into FYW divided by gamma M naught. So the reference is missed here. You can note down the reference as, in your notes, you can note down the reference as IS 800, page number 67, clause number 8.7.4. Yeah. See, the only last bit left here is the web buckling. Check for web buckling of the The check for web buckling will be done in the last video. Since this is not taken up now, because as we are not covered design of compression member yet. Once after the compression members is done, so then we'll come back and take up the check for web buckling in the last video. Thank you.